Okay, everyone, as I promised in the class, I'm going to go through some examples for you. I'm also writing a study guide for chapter 7. I'm almost done, but I'm also writing the solutions because I realized that would be much easier for you guys. And I encourage you to not look at the solutions and look at the solutions yourself, but I just included that to help you in case you don't know the solutions. So you have the solutions, but what I encourage you to do is to just read the bold part, the question, try to answer it, look up the book, and if you couldn't find that, write the solution. Anyway, so we talked about what is chemical reaction, what is the evidences, what are the evidences of chemical reactions, and why should we write chemical equations, and what is balancing a chemical equation and why do we do that. And now I'm going to mostly solve some examples. So first I'm going to talk about balancing chemical equations. Imagine you have CO2 plus H2O gives C6H12O6 plus oxygen. Remember, anytime you see an atom or element by itself, for instance, oxygen, you see O2. So although it has two atoms, but it's only one element, you do that the last. So now we don't consider oxygen. We can start with carbon and hydrogen. So first I start with carbon. I have 1 on the left. I have 6 on the right. So what I do, I add a coefficient. And as you remember, we don't change subscripts, because if I change subscripts, I'm changing the molecules and compounds, and we don't want to do that. So we just change the coefficients. So now I have like 6 carbon on the left, 6 carbon on the right. Next, we go balance hydrogen. You see we have 12 on the right, but 2. I just said the answer. So we have 12 hydrogen on the right, we have 2 on the left. So 12 multiplied by 2 would be 6. I put 6 on the left. Now we have like 6 multiplied by 2 equals 12. Hydrogen on the left, 12 on the right. And now I count oxygen. 6 multiplied by 2 oxygen, 6 multiplied by 1 oxygen. It would be like 12 oxygen, 6 oxygen. So it would be like 18 oxygen on the left. And now I have like 6 oxygen here. And in order for me to have like 18 oxygen, and then I have 6 here, so 18 minus 6 would be 12. So here I should be having 12 oxygen, but I have O2, so 12 divided by 2 would be 6. Now check the answer. So I wrote in general 6 CO2 plus 6H2O gives C6H12O6 plus 6O2. 6 carbon, good. I have like 12 hydrogen, good. I have 6 plus 12, 18. I have 6 multiplied by 2 is 12 plus 6, 18. So that is good as well. Let's do another example. Imagine I give you Al solid plus H2SO4 aqueous gives Al2SO4 3 aqueous plus H2 gas. So you see aluminum by itself, so you do balance this the last, right? And then your book says if you see an element that occurs more than one time, so if you have, like, for instance, aluminum on the right side, and then, or for instance, if you have like a compound that has like hydrogen here and hydrogen here, if it has like two eyes, you do it first. But here, I guess the example that I gave, we have like hydrogen by itself too. So aluminum and hydrogen we do the last. But let's start with SO3. The other thing to remember is that when you have polyatomic ions, you treat them as one unit. So don't separate them. That makes your life much harder. So now you have SO4, SO4. So you have 3 SO4 here, but 1 here. So you add 3 here. So now you have 3 SO4 on the left, 3 SO4 on the right. And now you can go, now you hydrogen and aluminum, you can just do either of them, but it's better to do aluminum because it's a metal. But I don't think it would make much of difference, and we can try it actually. So now I write this. So we know as a fact that first we should balance SO4. But let's say first we balance, or second rather, balance aluminum. If we balance aluminum, I say we have 2 aluminum here on the left, 2 aluminum on the right, and we have like 6 hydrogen on the left, and we should have 6 hydrogen on the right. Now, if in the above equation, or maybe I just here, if I first or second consider hydrogen, so I have like 6 hydrogen here, I put 3 here, and then I have 2 aluminum. So in this case, you see it doesn't make much of difference whether first you do or second you do aluminum or hydrogen, because both of them are just like elements by themselves. Let's do another. Imagine you have CH H18 liquid plus oxygen gas gives us HCO2. Actually, I meant to balance this equation, my bad. CO2 gas plus H2O gas. First of all, this is a combustion reaction because you have a compound mixed with oxygen and generates oxygen containing species. And then if you have like carbon and oxygen on the left side, and hydrogen, if you have these, usually you have carbon dioxide and water. But that's not always the case. It would be, you see oxygen containing species on the right. So we know as a fact we do balance oxygen the last, right? If you just know that, start with carbon, because as your book said, if an element occurs in only one compound on both sides of the equation, balance it first. So here, this is what I meant. So you have oxygen, so we agree to balance oxygen the last. But in general, if you had like for instance, here you have carbon that is just like in one compound, so we balance it first. On the left is on one compound, on the right is on one compound. But for instance, oxygen is like in 2 compounds, so we don't balance it first. So here we have 8 carbon, we put 8 here, right? And next, hydrogen, we have 18, so we put 9, that multiplied by 2 would be 18. And here oxygen, we have 8 multiplied by 2 plus 9 multiplied by 1 oxygen. And as you know, it would be 25. So I put 25 over 2, so multiply by 2 oxygen here would be 25. And now I multiply everything by 2, would be 2C8H18 liquid plus 25O2 gas gives 16 CO2 gas. Remember to multiply all the coefficients by 25. By 2. Plus 18 H2O gas. Unfortunately, I don't see you or can't hear you to see if you have any questions so far, but just email me and ask me any questions that you may have. So let's do another example. We are given Fe solid plus HCl aqueous gives FeCl3 aqueous plus H2 gas. Okay, we know as a fact that we balance H at last and then also Fe. So we start with chlorine. We have 3 chlorine on the right. I add the coefficient 3 here. 3, 3. And then we can worry about Fe. So I have one Fe on the left, one Fe on the right. Finally, I see 3 hydrogen on the left. In order to see 3 on the right, it would be 3 divided by 2 multiplied by 2, which would be like 3. And then I multiply everything by 2. Or like, I guess I write multiply by 2. So it would be 2 Fe solid plus 6 HCl. Remember to multiply by all coefficients. Gives 2 FeCl3 aqueous plus 3 H2 gas. Okay, let's write another example. So I have Ki aqueous plus PbNO3 aqueous gives PbI2 solid plus KNO3 aqueous. So here we don't have any elements by themselves, so we can just start from any of these basically. So I start with Pb. We can start with K, doesn't matter. I have one Pb here, one Pb here. I have one K here, one K here. And as you remember, here I have like 2 I, and here I have 1 I, so I add a coefficient of 2. Now you see the balance of K is, so K is not balanced anymore. So I should add a 2 here to have 2K. 2K, 2K, 1P, 1P, 2I. You see that now automatically I have 2I here. So that's good. And then NO3, here I have 2, here I have 2, 2. So the equation now is balanced. So this was about balancing chemical equations. So pretty straightforward. Now let's go about how to write different types of reactions. So we talked about precipitation reactions, and we said that if we have like 2 solutions and we mix them with each other and then we see a solid or precipitate, we call that a precipitation reaction. So imagine I gave you this reaction. And in order to predict precipitation reactions, you should know solubilities. So imagine I gave you this Ki aqueous plus PbNO3 aqueous. And then you want to see whether or not we have precipitation reaction, and if we do, what would be the products and how can we balance the equations. So we just balance that equation, so that won't be an issue. But in the sense of how to know if a precipitation reaction occurs or not. First of all, you dissociate the ionic compounds that you see to their ions. Here you see K plus, I minus. Here you see Pb2 plus, and O3 minus. And I encourage you go to the table of polyatomic ions and start learning them and memorizing them, especially the ones that you see. So you see nitrate a lot. It's a good idea to know now that the charge of nitrate is -1. And you can see that here too. So Pb would have been 2 plus and O3 would have been -1. So what you do here is that you want to have a chemical reaction, right? So you write the cation of one compound with the anion of the other compound. So if you were to have a chemical reaction, you would see KNO3. And also you would see PBI. Do you remember that we have like 2 plus for PB? So you should have 2 of I to have charge of -2. So you go to your solubility table, and if you remember, everything that has nitrate is soluble without any exceptions. The same thing for potassium. Anything that has potassium ion is soluble. So this is soluble in water. And what about PbI2? So you see in solubility table that anything that has I minus are mostly soluble, but they have exceptions. When any of these ions, including iodide, pairs with Ag plus Hg2, 2 plus, or Pb, 2 plus, the compound is insoluble. So PbI2 would be insoluble in water. So it forms precipitate. So now since you see precipitate here, you will be having precipitation reaction. So we write that as PbI2 solid plus 2K, or like so still I didn't worry about balancing the equation, plus KNO3 aqueous. So this was an example for this. Now, imagine you have Ki aqueous plus NaCl aqueous, and then you want to see whether or not you have a precipitation reaction or not. So write the ions K plus, I minus, Na plus, Cl minus. If you are going to have a precipitation reaction, this cation reacts with this anion. So you'll be having KCl, and you'll be having NaI. And now you go to your solubility table, you see that anything that has K and anything that has Na are always soluble. So you see aqueous, aqueous. Do you see any solid? Do you see any precipitate? No. So here you have no reaction. Now let's do another example. Na2CO3 aqueous plus CuCl2 aqueous. You want to see whether or not you have a precipitation reaction or not. You write the ions. Remember, Na plus CO3 2 minus. So you see, you see 2 here, so it has been the charge of this. You see CO3 has charge of, basically it has just one of that, so it would have been charge of Na. And Cu 2 plus Cl minus. You see, that would have been the number of atoms becomes charge. So if we are to have a precipitation reaction, we'll see NaCl and CuCO3. We know as a fact this is soluble for several reasons. It has Na. You see, if you dissolve sodium chloride, basically dissolved in water and stir it, if you put it in water and stir it, it dissolves. Now, what about CuCO3? If you go to the table 7.2 solubility rules, you see CO3 2 minus and PO4 3 minus are mostly insoluble. What are the exceptions? When either of these ions pairs with Li plus, Na plus, K plus, or NH4 plus, the compound is soluble. And we knew that we memorized that all of these are soluble, no exceptions. And now Cu is not among those. So this is insoluble. So it forms a solid, a precipitate. So we do see precipitation reaction. And now we want to balance this chemical equation. Remember, we have 2 sodium here, so I put 2 here. 2, 2. Good. Check. Na. Okay. What about CO3? I see 1 CO3 here. I see 1 CO3 here. Good. I see 1 Cu here, 1 Cu here. I see 2 Cl, 2 Cl. Good. Let's do another example. So I have been given LiNO3 aqueous plus Na2SO4 aqueous. You don't even have to write the ions. You see lithium and you see, didn't mean to do that, and you see potassium. You know lithium and potassium, whatever compound they form or whatever ionic compound that they form, it would be soluble. So you won't see any solid. So you have no reaction here. Let's do another example. PbC2H3O2 aqueous plus Na2SO4 aqueous. So you have Pb2 plus C2H3O2 minus Na plus SO4 2 minus. So the potential ionic compounds are like Pb SO4, so 2 cancel out, and NaC2H3O2 1, right? You know as a fact this is soluble. Now you should remember sodium. We said sodium, lithium, potassium, ammonium, nitrate, and acetate. These are always soluble, no exceptions. What about PbSO4? So sulfate is always or is mostly soluble, but when it pairs with calcium, strontium, barium, or lead 2 Pb2 plus, the compound is insoluble. So SO4 2 minus, mostly soluble when pairs with Ca2 plus, Sr2 plus, Ba2 plus, or Pb2 plus, the compound is insoluble. And as you can see here, it paired with Pb2 plus. So this is insoluble. So you see solid. So you will be having precipitation reaction. You see PbSO4 solid plus Na sodium acetate aqueous. And now if we want to balance this, and we should balance this chemical reaction, we see 1 Pb here, 1 Pb here, see 1 SO4, 1 SO4, 2 Na here, 2 Na here, 2 acetate, 2 acetate. Okay, somewhere along the line I forgot to press the record, so I'm not sure exactly when it got disrupted. But here, as I said, if we have like, this is like the precipitation reaction, so, or the subject of the precipitation reactions, how to predict them. Here we had like sodium and lithium. We know as a fact they are soluble, both of them, with any anion, so we have no reaction. So here we have like Pb, lead 2, we have acetate, we have sulfate, we have sodium. And we know sodium, so we write the constituent ions, and we know Na C2H3O2 sodium acetate is soluble because it has water, but for sulfate, we know that SO4 2 minus is mostly soluble, but, and if we go refer to table 7.2, is mostly soluble, but when pairs with calcium, strontium, barium, or Pb2 plus, the compound is insoluble. So for that matter, PbSO4 is insoluble. So we would be having precipitation reaction, and we write PbSO4 solid plus sodium acetate, aqueous, and then we want to balance the chemical equation, Pb1, SO4, we have one here, we have 2 sodium here, we added 2 here, and then 2 acetate, we have like 2 acetate here as well. And I was talking about is molecular equations, complete ionic equations, and net ionic equations. So molecular equations have equations that show complete neutral formulas for all the compounds in the chemical equation. So here we have like, AgNO3, and you see all of these are neutral. But for complete ionic equations, we have reactants and products as they are actually present in solution. So however they are actually in solution and present to participate or don't participate in the reaction, how they are actually present, if we write those versions, we will be having complete ionic equations. So for instance, if you have like AgNO3 in water, if you have like, if you have a beaker and then you have like water, if you put AgNO3 in it, you won't see like, and imagine, it has like most solids have like, or like ionic compounds rather have crystalline structures, so you won't see AgNO3s on the water if you dissolve it, because it is soluble in water. What you see actually would be Ag plus NO3 minus, NO3 minus Ag plus. And if you remember, we said like strong electrolytes, solutions, and strong electrolytes. So that is that concept. So by the same rationale, or if we consider this, we wrote Ag plus, NO3 minus, Na plus, Cl minus. And for solids, liquids, and gases, you don't touch them. You won't write them as their constituent ions, because if you have like AgCl and dissolve it in water, you actually indeed see AgCl, because it won't dissociate, it won't dissolve in water. And then you see that we have like some ions that they don't participate in the reaction, so we call them spectator ions. And if we omit them, we can write net ionic equation, which gives us the species that actually participate in the reaction. And the species refer to a kind or sort of thing. So when I tell you that write the name of all the species present in the reaction, it means all the reactants and all the products. And I see here aqueous, solid. Let's do another example. For instance, I tell you that write complete ionic equation and net ionic equation for the following reaction. So we say Pb2 plus NO3 minus. So as you see, writing these ions is chapter 5. So that's why I was emphasizing a lot, chapter 5. And then for LiCl, you say Li plus, Cl minus. But you have 2 of those. So it would be So first let me write all the ions and then we come back to this. Gives you PbCl2 solid, you won't touch that, plus Li plus NO3 minus. Now you have 2 NO3, you put 2 here, right? You have 2 Li and 2 Cl, right? Because it's as if it multiplies by both of them. You have 2 Li and 2 NO3. So this would be the complete ionic equation. And as you see, 2 Li, 2 NO3 are your spectator ions. So if we omit those, it would be Pb2 plus aqueous plus 2Cl minus aqueous gives PbCl2 solid. So this would be your net ionic equation. So now let's do some acid-base reactions. So in acid-base reactions, you have an acid, usually have H plus NaOH, a base, usually have OH. They react and then they produce water and salt, or an ionic compound. So you see, in your acid, you usually have, or always rather, they generate H plus. And in your bases, you usually have, or I guess it's fair to say that most acids have hydrogen and then most bases have OH. Or at least for the ones that we consider in our course, acids have hydrogen, bases have OH. And they produce, if you see you have if H plus OH, you see you have 2H1O. So this water comes from these two. And then this anion and this cation would form an ionic compound. Now let's do some examples. So for instance, if you have H2SO4 aqueous plus KOH gives what? So you see here you have acid because you have hydrogen. Here you have a base because you have OH. So you see H2O liquid, water, and in an ionic compound that has K and SO4. SO4 have a charge of -2 and K has charge of +1. So the compound would be K2SO4 aqueous. And now balancing the equation, we have 2 hydrogen on the left, 2 hydrogen on the right. We have we have 3. You see? So we have, let's see. So it's better. So this is an example of, it's not a good idea to start with hydrogen, because you have in multiple compounds. So what I do, I start with K, potassium. I have 2 potassium on the left, so I put 2 here, so it would be 2. I have 2 on the right, 2 on the right, so I put 2, so I have 2 on the left as well. What about SO4? I have 1 on the right, I have 1 on the left. And what about oxygen? I have 1 on the right, but I have 2 on the left, so I put 2 here. So I have 2 oxygen here. So let's check again. I have 2 potassium on the right, 2 potassium on the left. I have 1 SO4 on the right, 1 SO4 on the left. And now, what about oxygen? I have 2 oxygen on the right, 2 oxygen on the left. And remember, this SO4 we treat it differently, so don't be confused by oxygens there. Now what is remaining is hydrogen. I have 4 hydrogen on the right, and as you can see I have 2 hydrogen plus 2 hydrogen, 4 on the left as well. So I'm all set. And that's why it's a good idea to not start with hydrogen, because it's in multiple compounds. Let's do another example. HNO3 aqueous plus CaOH2 aqueous gives. So now you see this hydrogen, you should be able to write this. And then you see OH, you know this is an acid base reaction. So I write H2O plus, and then you have CaNO3. You know that Ca has charge of +2, NO3 has charge of -1, so you should have 2 of that. CaNO3 2. H2O is liquid, this is aqueous. So now let's balance this equation. So we have 1 Ca on the right, 1 Ca on the left. We have 2 NO3 on the right. I put 2, so I have 2 NO3 on the left. I have now how many oxygen? Remember, we already dealt with this. So now let's count. So you see hydrogen is in like 2 compounds, so we start with or resume our work with oxygen. Here I have 1 oxygen, but here I have 2 oxygen, so I put 2, so I have like 2 oxygen, 2 oxygen. Now for hydrogen, I have 4 hydrogen on the right, I have 2 plus 2, 4 hydrogen on the left, so I'm good with hydrogen as well. It would be 2, 1, 2, 1. And now if I tell you to write complete ionic equation for this equation, what you do, you write H plus aqueous plus NO3 minus aqueous plus Ca2 plus OH minus, and then you have 2 of that, remember. Aqueous gives 2H2OL. We don't balance, we don't touch, or we don't dissociate liquid, solids, gases. Plus Ca2 plus NO3 minus, and we have 2 of that. And then I multiply these 2 by the parentheses as well, so I don't have to write it again. So that would be it. And if you look at it, and then you can always double check to make sure that you have 2NO3, Ca2, 2H2O. Okay. So you have Ca2 plus here. You have NO3 minus. So these are your spectator ions. If we omit those, you have 2H plus aqueous plus 2OH minus aqueous gives 2H2O liquid. And this is H plus OH minus gives H2O, the net ionic equation for acid-base reactions. So still we have oxidation reduction reactions, combustion reactions, and then classifying chemical equations. I think I can just give some examples of those, and we have like gas evolution reactions too. So I think I record another lecture with these ones. I just don't want to make this lecture or this problem solving lecture, I guess, so long. So see you guys soon.